Oh, what a mess. This is Neil Schneider from Meant to Be Seen. Welcome back to my messy basement. Now, in the last episode, I talked about Disney Plus and how you couldn't do surround sound on PC with Disney Plus. And I was going to explain in this episode how to actually do it. Well, it turns out I learned even more since that last episode. And what I decided to do is to spend a full episode partially on Disney Plus and other services and to how to enable them in really interesting ways. But I'm going to do that in the next show. And the reason is I'm expecting some equipment in the mail. It hasn't arrived yet. So I just want to make sure I have everything so I can do this properly for you. With that being said, I have a very special episode of Neil's Messy Basement for you today. Joining us is Jarl Ostensen. He is the Director of Engineering for a company called Polystream. Now, if you've been tracking Meant to Be Seen and my work, you know I'm very excited about something called the client-to-cloud revolution. And what's happening is our devices, our smartphones, our PCs, our consoles, other devices as well, are being further enabled by cloud technologies. And the idea is that we're able to do more than what our devices are naturally built with. Now, Polystream is a very important player in this market, and you're always going to talk about the next era of computing, what they're excited about, how their technologies work, other things going on in the market. Really exciting stuff. So we're going to be back with more right after this. Welcome back. To my immediate left is Jarl Ostensen. He's Director of Engineering for a company called Polystream. Really excited to have Jarl here today. Welcome to my basement, Jarl. You'll forgive the mess.
Thank you very much, Neil. I'm very happy to be in your basement, virtually.
So, everybody knows I'm very excited. We call it the client-to-cloud revolution. There's all kinds of compute models out there, but really, I'm excited about where computing is headed. Things are. I think you'd agree. Things are changing as how compute is done. I'd like to, of course, we want to hear about Polystream. And before we go into what Polystream does, I was hoping you could elaborate a little more as to how computing is changing over the coming years. Are we going to see dramatic changes in how we use our devices and what our devices are capable of?
I think we will, and I don't think I need to be particularly perspicuous or have a crystal ball, to be able to say that. Predicting the future is always hard, but I think one thing that I can jump straight onto is, for example, what's happening in terms of hardware evolution to support the growing demands of AI everywhere. And we have mobile devices with neural processors to be able to make decisions and to use neural networks for on-device decision making. We obviously have a tremendous amount of compute being created in the cloud to allow for incredibly complicated problems to be tackled. And it's someone said a while ago, and I think it was related to the whole COVID situation, that we have a poor grasp on exponential growth in the area of compute, and especially the AI domain. I think exponential growth is exactly what we're facing. So I don't think we can really predict what's going to happen in the space easily, but it certainly will grow, and it will grow incredibly rapidly. And there is a tremendous crossover with hardware and software, obviously, right? So I also think, because we're getting to that point, everyone says Moore's law is we're getting to the point of diminishing returns. It's certainly changing, right? And we're certainly coming to a point where the universal processor, the processor that can do a lot of work for a single thread and sort of run everything from games to spreadsheets, that era is probably coming to if not an end, then at least it's coming to a point where it has to be augmented by specialized hardware, and we're seeing a lot of that. We're seeing, growth of custom FPGAs in the cloud. We're seeing the ascent of RISC-V. Who knows where that's going to go? We see the GPUs being used, especially for AI, and as I said, the neural processors on mobile devices. So What I do know is it's going to change. It's going to change a lot, and it's going to have a tremendously positive impact for what we are able to do as consumers and users of everyday technology.
Well, okay. So there's a lot going on. Maybe we could speak at a more even a more fundamental level. So in today's day, I mean, I've got my smartphone device, I've got a PC, I've got a console, and they're all pretty much self-reliant. Okay, like they're all, you know, if I didn't have any internet connectivity, I'd probably be able to use most of my devices, you know, without trouble. But but the thing is, I'm limited to the power of those devices, right? I'm limited to whatever those devices are built with. What's changing? How if is the next era of computing going to look different than that?
Yeah, it's a great question to ask, Neil. And of course, you know, you're right. It will on its own, and it's been like it's interesting actually. As a sort of slight tangent, but relevant to that, I have occasionally I think back at the days when I had a computer that wasn't connected to the internet, and I sort of keep going back thinking, how on earth did I do anything? You know, and I was running MS DOS, and I had I integrated my assembler and my compiler there. But how could I do anything without an internet connection? And because this day and age you can't really do anything at all, and you can't really imagine doing anything without being connected. All of that compute power, all of that exciting innovation is going to be meshed together, right? It is already being meshed together. It's going to be meshed together. We have the Internet of Things. We have the intelligent edge. They're all merging together. We have the idea of a 5G network that can give us the ability to actually run a very broad range of applications. So, yeah, I mean, to your question, all of these innovations, all of these hardware innovations, for example, they will all be part of a ecosystem innovation, which is the meshing together of all of that compute across every device, every part of our lives, really, I think.
So, you know, I'm holding up my smartphone. Today I think of a smartphone as the smartphone, but really what I'm hearing, if I'm hearing correctly, is in the future when we're buying our smartphones, we won't be just thinking of the device. We'll be thinking of all the compute, all the abilities connected to that device. That's the actual product.
Absolutely, it will be. You can imagine that your smartphone, your phone will be. You will always think of it as part of a very large compute ecosystem, and you know that you always have available to you. Maybe the consumer doesn't consciously think about that, but they will have a tremendous amount of functionality available to them. And I mean, it's wrong to say that phones or PCs become dumb terminals, because of course they're not. They are part of that entire mesh, but they will be always connected in a way which allows you to take advantage of, you know, a data center nearby or an edge node nearby, and to be able to do things that, of course, the individual device just couldn't do. Autonomous cars is, you know, the obvious example, perhaps, and their ability then to start communicating with over 5G to local nodes or nodes in the nearby area that can help make complicated decisions and feedback traffic information, etc. So yes, it will be. I think it'll sort of blur the whole picture really about, you know, our localized compute and what we today call remote compute, which still is a little bit the realm of those people who know how to set something up in the cloud, perhaps, or, you know, yes, you do it when you access a web. Well, when we're doing Skype, for example, but it will become much more a natural integrated part of what everyone does. I mean, I'm teaching my daughters some coding using Minecraft, for example, and through those things as well, they are already starting to understand that there is such a thing as a connected world. There is such a thing as a cloud. And that's going to be ingrained in how new generations are thinking about how they do anything with computers. I think they'll probably stop thinking about them as computers, and they'll just think about them as parts of life.
So I want to differentiate. And please feel free to agree or disagree. Right now, when we buy our smartphones or we have a PC or a console, we are already connected to the internet. We're already having benefit from cloud computing, and things are being done in the cloud, like we're getting information and the web and so on. What we're talking about is our compute devices will actually be able to do even more. That we're talking about you doing even more than what we're experiencing today, via like sharing and responsibility between the compute, being able to get compute from a distance that we otherwise wouldn't have access to. Is that am I correct? Is that a fair analysis?
Yeah, that's a good way of putting it. You can imagine that we'll be building applications that are not just built to run on a single device, but they're actually built to run across multiple devices simultaneously. In other words, devices that in many ways sort of similar in mentality to how a mobile phone has, this split between big and little cores, the big compute core that does heavy lifting, the lighter ones that can do low powered work, etc. You can imagine that you break open that mobile phone and you start thinking like that across your PC, your laptop, your phone, your tablet, that they all actually are interoperating for running some of the things that you're using, some of the applications you're using.
So when we opened up, you brought up about neural networks, artificial intelligence. I think you mentioned FPGA processors. I hope I'm hearing the terminology correctly. Now that we're talking about this model of, let's say, collaborative compute, both locally and from the cloud, how do those technologies fit in? Why did you bring those technologies up?
I think partly, as I was saying earlier, because the sort of the era of the single big CPU that does all the work and it can be used for anything, the sort of universally applicable processor, that is inevitably coming to a point where it's no longer we're not getting the doubling in performance or the quadrupling in performance that we used to have with every generation. So we inevitably have to move into more specialized piece of hardware, and GPUs are a great example of that for machine learning, where you can run machine learning on a traditional processor, but if you build a machine learning algorithm that is running on a GPU, on a big vector processor, effectively, you get much bigger results and faster results. And in fact, arguably, GPUs have unlocked the AI revolution because suddenly it is possible to do this. AI, machine learning on neural network algorithms, most of them have been around since the 60s, and they're not, many of them for a long time never really changed much, but there was a practical limitation to how much you could do with it, because you couldn't, your computer would sit there and melt after a week or so and just not get through the problem. Suddenly you can run these things in a matter of minutes, perhaps. And that's unlocking it, but it does prove that we have to move into that space with specialized processors, specialized hardware. Even things like if you sort of look out into the industries, there are things like compute memory, as in moving units of compute closer to the actual storage itself to be able to do some processing just before it's stored in memory. There are the growing, incredibly intelligent NICs, network connectors and routers and switches in a data center with their own processors and OSs on them, doing a lot of processing outside of what's being done by your CPU. So it's kind of, in fact, I'm going to show you something because I have it in front of me. This is actually an 886. This is the first. I'm not going to take another bag, but this is an 886. You can just roughly see it there. That's my first. That's my first CPU that I have.
8086, right? The Motorola.
That is really thick, yeah, and a few pins there.
I just grew extra gray hair, by the way, while you were showing that chip. I just sprouted out. Oh my goodness.
And and then here's I think there's a Core 2 Duo Intel processor, which is a lot more recent. We moved from this piece here, which can do some calculations. We moved to this piece here, getting more and more clever. They're getting bigger and bigger. But now we are actually coming to a point where we are arguably moving to the side and bringing back some of these smaller, more compact and more specialized hardware pieces, because we have so much more work to do, so much more exciting calculations that we need to work out. Trying to run them all on a single piece of hardware is just not the way forward anymore.
So we're gonna talk about Polystream very, very shortly, and before we do, I just want to highlight, there are companies out there that are doing, cloud streaming, cloud gaming, where nearly 100% of the responsibility is in the cloud remotely, and these, and they make it possible for content to run on all kinds of devices, be it smartphones, tablets, PC, console, you name it. In your experience, what are the challenges when it comes to, enabling technologies like that?
Well, there are quite a few different challenges. So one is, which is, I don't think it is controversial, although it might sound a little bit controversial. One is the slowness of innovation. So, if you want to move game experiences into the cloud, you can do that by saying, okay, I'm going to take what I've given you on your desktop and I'm going to serve it from the cloud. But actually, that's kind of missing what you can do. And back to our earlier conversation about meshing this growing compute that's available to you across different devices, etc. That's not really taking advantage of that anymore, right? That's still the old idea of I'm running it on my one device. Of sort of, this is my leaf node, and I'm not really, once I've downloaded it, I'm running it locally, and that's it. So there is a big challenge there about taking advantage of new technology, not just using it, but taking advantage of it and seeing the kind of potential that it unlocks. And taking a game today that fills up your hard drive pretty quickly, and moving that into the cloud and making it even bigger because it can be run on, a data center and servers in the data center with lots of storage, lots of memory. That's a step of innovation that we need. We need, just like AI is embracing new technology very, very rapidly, we need games and other 3D interactive content creation industries to embrace the potential that they have when they move into a fully connected, across devices and cloud-enabled kind of reality, which we already are in. So that is one challenge. That's just that inertia, which was always there, I suppose. But it is just one thing to keep in mind. The other challenge is currently is technological. There are some limitations to how you can do the streaming with current technologies. You want to reach millions of players. You want to reach them across the world, not just in the sort of the Silicon Valley hotspots or center of Europe hotspots. And you want to reach them in parts of the world much wider than those. And so you need to have accessibility of resources. You need to have the scalability of resources, and you need to be able to manage, to some extent, cost. And those are challenges that I think traditional and current cloud gaming streaming have.
Is it feasible that this class of compute distribution, if that's what we want to call it, is it possible for it to reach millions and millions of people at a time? Is it are there challenges there?
It is possible for it to reach it. I mean, you have obviously the question of network infrastructure and getting it to the actual consumer, to their homes, to the last mile. But that is a increasingly covered. That's being increasingly covered around the world because of the fact that we are depending so much on having cloud compute resources for even our daily lives, whether we know that we have it or not. So it comes down, in fact, in some ways, perhaps it is ironical, but because it comes back to the problem of some of the specialized hardware that it's not necessarily out there yet. We still need to be able to build a lot of what we want to run. We still need to be able to build it on hardware that is ubiquitously available. So when it comes to cloud gaming, for example, it's very important that if you want to reach a large audience, that you are able to do that on commodity cloud hardware and not have to necessarily go into using very specialized pieces of hardware, which are still not available everywhere. They will be at some point, perhaps, or some parts of it will be, but it is very important to be able to reach by using the commodity, the enormous amount of compute. I don't know how many flops are available out there in the cloud right now. Someone has actually made an estimate of it, but it is a tremendous amount, and so being able to use that is important.
Well, we've been talking about compute, and the other side of the coin that's equally important is the distribution. And something I've observed, there's a lot of enthusiasm around 5G. I mean, it's the next generation of wireless distribution. Everyone's excited. It's being implemented. And yet, maybe it's a different problem, but during this pandemic, what's happened is a lot of the leading, cloud service providers, they've scaled back distribution. Like they cut back how much they're streaming, how much bandwidth they're using, and with this, if you want to call it a grand vision for the future, is there enough bandwidth to go around? Is it really a finite resource that we always need to think about?
That's an interesting question. I think it's a great question because I think we know that part of it is economy. And part of it will be actual technical limitations. The technical limitations, I am absolutely confident we can work around and we can unlock the bandwidth that's needed. We can get to the point where that capacity is there. As I said, switches and routers in the data center are the hundreds of gigabits that they're starting to push through is not slowing down, right? That's just increasing. And so the ability to pump the data in and out is definitely there. I think, quite frankly, and 5G is an example of this, one of the biggest problems is that it starts involving regulators, it starts involving who owns what rights to which part, how do you monetize it, how do you price it, who pays for which bit, am I paying for the pipe into my house and then the content, or is it a combined thing? So when it comes to providers having to throttle back, I think that is largely an issue of economics more than technology.
Okay, so now we've set some groundwork of where compute's headed, how we can start thinking of how our devices could be working. We've talked a little bit about the bandwidth, or where it is today, versus where it could be going. Let's talk about Polystream. I mean, what does Polystream do? Why is Polystream so important in this ecosystem?
So first, maybe say a little bit about how it came about. So our CEO, Bruce Grove, he was at OnLive, which 10 years ago launched the first game streaming service using video streaming. And OnLive did not succeed. They struggled with the economics of using GPUs and having to build custom racks and wheel them around close to customers, etc. And I think Bruce said at one point that after that he wanted to have nothing to do with streaming anymore. That was it. He was done. But then about 5 years now, I suppose, ago, he met with our CTO, Adam Billiard. Adam Billiard, I know him from the past. Him and I worked together at Renderware. He was one of the founders of Renderware. And he had invented a new way of doing this, which we now call command streaming, which instead of sending pixels, instead of scraping pixels on a server, you send commands that are then destined for the client device GPU, and you render it there. So there's no need for GPU on the cloud device. And he met Bruce, and he basically told him that the reason why OnLive failed was because you were doing it all wrong, and here's how you should do it. And Bruce saw that this was actually a good way of doing it, and Polystream was created. And we have now, over the last 4 years or so, we've built up this technology. And the fundamental idea of it, and the reason why I think it is important for the revolution of getting more and more content to be cloud native, to be cloud first, is that it addresses the issue of not needing. You can run your application on any VM. All you need is the base compute. You don't need a GPU, which means that suddenly you can reach any data center. Many data centers don't have GPUs. They're also extremely expensive for lots of reasons. And now you can serve these applications everywhere, and you can stream the data down to a client device where it's then rendered using its own GPU. So how it's sort of conceptually different from pixel streaming or video streaming is, with video streaming you've sort of taken the cost hit by paying what it cost someone to have a GPU in the cloud, to power it, to have it there sat in a rack. Your end device only really needs to be able to render video. So of course the cost of that device can be pretty low, but you are paying that fee for being able to use that service. With command streaming, you pay very little for the cloud service, and you have presumably a capex that you've covered by buying your laptop or your PC or your Mac with a relatively decent GPU in it, which, you know, for all intents and purposes, all modern devices are not even that modern, but all devices from the last 5 years or 10 years have pretty good GPUs in them. So the two solutions, our solution, Polystream's command streaming solution, can scale at a rate that GPU streaming just cannot do, because you can't get enough hardware in the cloud to do that, and reach at a much broader reach for that reason. Cost is also lower, but they can live together. I think the future is a hybrid world together, where, you know, if you want to have that quick, I just want to look at it on my iPad. I want to have a quick look at this model. I want to rotate it around. I want to zoom in and out. Maybe it's an architectural model. You know, I'm in my kitchen at the moment. Then video streaming works really well. If I'm actually going to do some work on it, or I want to look at it on my laptop, which has a bit more power in it, I want to do more interesting lighting perhaps, and actually do some changes to it, content creation work, then command streaming is the best way. Also because, you know, everyone talks about latency, and latency is a function of distance. If I can run it out of every data center, then I can reduce the latency because I can be much closer to where you are. I can also start taking advantage of the edge, because I don't need an edge node with a GPU. I just need an edge node with compute. So that's the sort of the general gist of what our technology does, and why I think it's so important for where we're going.
So, well, why don't we elaborate a little more on the bits and pieces, so as everyone will fully understand. So, including myself. So with a traditional, let's use cloud gaming as an example.
Yep.
So cloud gaming, as I understand it, is for each individual user, so each gamer, they need a dedicated, if you want to call it a computer in the cloud, or a dedicated graphics card, or, you know, like a hybrid CPU, GPU, but they need dedicated resources just for them. Does that, so you need, so for, if you have 1,000 gamers playing at the same time, you effectively need 1,000, you know, computers in the cloud. Like it might be homogenized and you divide the resources, but the point is you need dedicated GPU, CPU resources for individual gamers.
Yeah,
and I gather, so that's correct, yeah?
Yeah.
Okay, so I gather a big challenge with that is, how, you know, do you have enough GPUs in the cloud? Is there enough there to service the need of thousands, if not millions, of gamers at the same time?
Exactly.
So what Polystream is doing, if I'm hearing correctly, is it's saying, okay, well, we don't need the graphics equipment in the cloud. It's enough to have the CPU processors. Okay, so the CPU processors, you call it command streaming, right? That's what I heard. Yep. So I gather these CPU processors are sending commands, okay, and they're sending it to our personal devices. So our devices are our smartphones, our PCs, our consoles, and that's where the graphics are. And I gather, and different devices have different graphics abilities. Is that correct? So now the question I have is, why is this so much more scalable versus CPU, GPU in the cloud?
Yeah, so you touched on it in the beginning when you were summarizing it. You know, imagine sort of in a slightly simplified way, if I want to get a GPU, if I want to do a GPU streaming solution, I need to get a CPU resource, you know, however many cores, and a GPU resource. These two things are not the same. They are two different pieces of hardware. So I need to, first of all, get this particular instance that has that piece of hardware. So that immediately reduces how many I can get. It just does, because there aren't that many that have both of them. Because more people, most of the data center workloads out there are non-graphical workloads. So, most data center server instances don't need a GPU because most of the work is being done on them right now. If you ignore if you look aside from the AI bit, which isn't a graphical workload, right? It's a compute workload. They don't need that, so they only have CPUs or have CPUs available. CPUs are also very easy to share. Very, very easy to share that through virtualization technologies, etc. It's very easy to share it. You can have lots of different users using the same resources because most of the time they do no work. They're idle. Whereas with command streaming, because you only need that CPU resource, you have now eliminated the need to allocate yourself a GPU out there, of which there is a limited number. So you're no longer restricted by that factor. You can go to any data center that has available some compute, which every data center has. As an example, we have been running our technology on data center providers that, well, at least for me, before I joined Polystream, I'd never even heard of them. I'd heard of Amazon and Azure, and I heard of Google Cloud, and maybe I'd heard about Alibaba, but you hadn't really heard much about all these. There are a plethora of different data center providers out there in the world, and they have compute. They don't have GPUs because they're very expensive to install and manage. So the scalability comes down to availability of resource. There are just not that many graphically capable and graphically dedicated GPUs available for this kind of work. Also, the problem as well is when you're not doing rendering with a GPU, you have to get something for it to be cost efficient. So, you have to now slice this time between perhaps some heavy AI workloads and your game running workloads. So you get the problem of when there might be heavy resource contention, for example, whereas with pure CPU resources, they are quite fluid, if you like. It's very easy to move around and find these things in data centers. So the scalability from using our technology comes from that. It's basically the benefit of running on available commodity resources as opposed to specialized resources.
All right.
Does that make sense?
Yes. So if we were to think about this just through, let's say, a traditional PC, we do have a relationship between the CPU and the graphics chip or the graphics card. And this is what PCs and computers are doing today, right? The CPUs are sending commands to the graphics card, but I imagine there's a lot of commands going on. It's not PCs are rated as far as their bandwidth and the communication between the CPU and the GPU. Doesn't that have, aren't there concerns with that if you're suddenly going from something that fits on a motherboard to a distance of possibly hundreds of miles apart? How do you get all those CPU commands to the graphics card fast enough that they could get work done?
And this, quite frankly, is the reason why I think no one else has done this. I think because if you do the back of the envelope calculation, modern PCI Express buses, they're just going up and up and up. You can pump hundreds of gigabytes of data per second to a GPU if you want to. And obviously, that's not going to work over a network connection. So, yes, there is a challenge there, and we met that challenge with our proprietary compression technology, which quite frankly is, I'm biased, but I'm going to say it's pretty amazing because it is able to take those enormous data sets at runtime. So we do this processing in 4 or 5 milliseconds and send that down a 25 megabits per second or 20, or in some cases lower, less than 10 megabits per second pipe and having rendered. So it is purely possible, only possible because of our compression technology. Otherwise, it would be madness, which is why no one has done it before.
Okay, so what I'm gathering is it is similar data to what you're getting on a traditional motherboard. It's just what Polystream is doing is they're compressing it to something that works. And well, you have proof of concepts, right? I mean, you guys have been busy. Let's talk about Life is Strange 2. I mean, that's a game by Square Enix, and it's a demo that the game's been around for a while, but there's a demo out now that's using your technology. Can you
Yes.
elaborate a little more as to what it's doing, how it works?
Yeah, I mean it's I mean in some basic way it's doing exactly the same as what we do for the other titles that we have out there, and we have Life is Strange, we have Walking Dead, Rocket League, we also have the Unreal editor and a few other things like that going to just show the breadth of things that we can stream this way. And it is, as I said, it's basically sitting there in a virtualized environment. The game itself has no idea that it's running in a special environment. It thinks when you set up a session, when you connect as a user, the game itself is under the impression that it's running on whatever graphics hardware you have on your local device, right? So if you have a 1080 Ti, then that's what it thinks it's running on, and it's basically just sitting there, as I said, as a sort of API virtualization layer, taking the data that the game Life is Strange is pumping through to the graphics APIs and down to the driver level, compressing it, sending it, unpacking it, and rendering it. The client that runs on the device is a generic client, so it runs, the same client runs all these different applications. And in fact, from the point of view of the actual technology, the game itself or the application itself has very little nuance and differences in terms of what the engine itself does. Our compression engine is fairly generic. So yeah, it sits there and does a 2 orders of magnitude or more in some cases compression job and pipes it down to your device. That's what it does.
So are there any trade-offs when using the technology? So I'll give you an example. So I ran the Life is Strange 2 demo, and but you couldn't really adjust the settings. Like, you were locked out of configuring the game. Was that just because it's approved? Like, do you want something out there, or is there really a lot more flexibility if it was just coded?
There is more flexibility. It's we deliberately. It's interesting when I first tried on live with Crisis 2 or Crisis 1, perhaps it was many years ago. The first thing I did, and that's the first thing everyone does, is you go and adjust the settings to see if you can break it. There are some things around how a game deals with changing settings which can cause an issue, and it's not a fundamental problem. It's more the fact that we are still a small team, and there is some limit to how much capacity we have to fix all the edge cases. So in the case of that, it was the safest is just to disable the settings. But that's not a fundamental limitation. That was purely a choice we made just to make sure that we didn't get too many issues that we couldn't just immediately deal with, so that in case people had a problem with it. It's also, if you're running on a device, there could be issues around drivers, etc., that could exacerbate that. So the safest was to disable it.
I was impressed when I ran the demo. I mean, first, of course, it's the game itself. That's an experience in itself. You're gonna have to check it out. But what immediately impressed me was how instantaneous it was to get the game running. Like, there was barely an installation process at all. I don't think there really was one. It was just, play, and that was it. And you're right in the game. So how do you, from Polystream's point of view, when it comes to marketing the service, what are the key takeaways? Like, what do you want people to know about Polystream today?
I think there are a couple of things. I mean, we started out actually with that sort of instant accessibility angle, and it's obviously very interesting, especially for games companies, because they lose a tremendous amount on the sort of their acquisition funnel is deep and broad, right? They lose a lot of people from that point of bringing them to a website or a call to action to actually get them to download or even get them to run something. So having that instant, I can click the button and, as you said, it just runs, is a tremendously important thing for that, especially for that industry. The other things as well, as we were talking about briefly earlier, is the ability that you now have to actually start building cloud-first or cloud-required experiences with a model of scalability that is interesting. I mean, for the games industry in particular, scale really matters. They're not interested in a couple of hundred people coming onto their service or even 1,000. They want more than that. And so for them, it's very important that they can do something quickly that can launch a very, very large number of people without breaking the bank, which is what traditional methods would do. So I think for us, aside from all the marketing thing, I think for us, one of the really important messages is to make people understand that this works. Because it is really a little. It is one of those things that, because no one has thought about doing this before, and no one has thought that this is possible, it is sort of seeing is believing, and the fact that we have it working, we have it, as you've tried as well, demonstrably working, and I think this is incredible. It's incredibly important that people start thinking about that and really, embrace and understand that we have here a piece of technology that unlocks opportunities that we just do not have today. So I think that for us, the big topic of every day is how do you message that? How do you, when you have something that is so groundbreaking and so different in terms of how people think about what you do and think about, their assumptions are quite deeply ingrained about how you should do this, because FFmpeg has been around for 20 years and people have had lots of time to play with it, so it becomes the sort of the default stance. Getting it out there that here is a way of doing it which resolves all of these problems of scalability and has the same level of, or better level in some case of reach, is just incredibly important for us. But it is an interesting challenge that new technologies and new ways of thinking, they aren't always easy to get across. It's remarkable actually how often you find yourself in that situation where you realize, when you take a step back, that actually this technology does seem almost a little bit unbelievable sometimes, and you have to sort of work that into your way of thinking and making sure that you take everyone on a journey. And that's the thing that I think is very important, absolutely very important for us, because I think it will genuinely have a big impact on not just us but other industries as well that can use this kind of technology.
And you're mentioning other industries. I was just going to underscore what we're talking about. I know we've been talking about cloud gaming, but this is really about computing in general. Like, this is about all kinds of applications in compute. It's not at all. I don't think it's at all limited to gaming. Am I right?
Yeah, you're absolutely right. I mean, we're doing some very interesting work with a university and some financial institutions here in England, for example, for the ability to run very, very large financial modeling, so compute workloads in the cloud, and being able to visualize those on a device. That runs up against exactly this kind of problem where you want to run this massive cloud-first workload, and you don't either you don't have access to, or you really don't want to spend the money on hosting those in areas where you have GPUs, so that you can do some visualization occasionally. You want to be able to run this and visualize it freely at no extra overhead and no extra compute cost. And that's an area which is super interesting for us. The same goes for molecular biology, which obviously is pretty relevant these days. Again, it's about visualizing very large data sets. Reservoir modeling in the oil industry is another example, right? So the games industry is just one of the verticals. We are in games. We are also with simulation and training, working with the Ministry of Defense, and in areas such as finance. And if we can contribute something in those areas, then that's great.
Now, I know Polystream on its own has fantastic technology. I mean, as you've described, would you say that this is something that would benefit from ecosystem development? Like, do you see a lot of ecosystem getting involved to enable compute like Polystream?
Yeah, I think so, because ultimately, I think so, because ultimately the ecosystems, if you develop an ecosystem in isolation, then that's not going to last very long. An ecosystem becomes an ecosystem because of participation and because of inspiration and input from a broad range of people and other industries and ideas, etc., and problems. I think I would like to see in the future that there are standards developed that can take advantage of this kind of thing, for example. And I know we talk about these things a lot, because I think that's when it starts really being able to pick up and become valuable. And it's open source is also a very important part of that future. I think in some way, I think that the tremendous acceleration of innovation you get from being able to share ideas and to be able to have other people explore those ideas and build on those ideas is truly exponential. And I think I think that's a very much part of what needs to happen at some point in the future.
I'm going to brag a little bit, and you're going to mention that Polystream is a member of the International Future Computing Association, and it's always good to brag after you talk rather than before you talk. It's a pleasure to work with you regularly.
It's worth bragging. It's worth bragging about. I think I think the TIFCA initiative is tremendously valuable to us for exactly these reasons, right? It's not just about. It's about. This is more about more than just us. It's more than just our business and what we do on a daily basis. It's about thinking ahead and trying to envision, as you have been doing with TIFCA, and trying to envision a future and the ecosystems that we need to, not to sound too dramatic about it, but quite frankly for coming generations to be able to actually take advantage of these things in a way that that really works for everyone, is accessible, and doesn't break the bank.
Well, thanks for joining us, Jarl. It's been great having you in the basement.
Thank you, Neil. It's been a pleasure. Absolutely.
Wonderful. Well, we'll be back with more right after this. Thank you for visiting me in my messy basement. So I will be back next week. We're going to talk about, as promised, I know I'm going to deliver this time, how to get surround sound working on PC with Disney+. But more than that, we're going to talk about how to get the most out of other streaming services as well. So we'll be back again next week. Thank you for watching.